The following set of questions are going to be asking whether the series converges or diverges, and they are all perfect candidates for the ratio test because of the presence of a factorial or an exponential function, and the reason that this is part of your bell work for today is because the ratio test is used exclusively when deciding whether a power series converges at a point, converges absolutely, or converges over some interval. So we're going to review the ratio test because we use that as the first step of the new lesson for today on whether or not those power series converge at a point absolutely or over an interval. With that said, if you were to do number 1 here, to set up the ratio test to decide if this series converges or diverges, you start with the limit as n approaches infinity of the absolute value of a sub n plus 1, which is n plus 1 factorial divided by 2 raised to the n plus 1 power, divided by a sub n, which is really times the reciprocal of a sub n. And before we evaluate this limit, we simplify it. So as a refresher, n plus 1 factorial is equal to n plus 1 times the next integer down, which would be n, times the next integer down, which would be n minus 1. And you would continue until you get down to 1. N factorial is equal to n times the next integer down, n minus 1, times the next integer down, n minus 2, all the way down to 1. So if you were ever asked, what is n plus 1 factorial divided by n factorial, this is what you would be considering, and they have a lot of common factors that cancel out so that you're left with just n plus 1. So this n plus 1 factorial divided by n factorial turns into just simply n plus 1 in the numerator. 2n divided by 2n plus 1, there are a couple of different ways you can think about this. One way to think about it is 2 to the n power divided by 2 to the n plus 1 power. You are dividing common bases, and when you divide common bases, you subtract your exponents. So it would be 2 raised to the n minus n plus 1 power. Remembering to distribute that negative sign, this becomes 2 to the n minus 1. So your n's cancel out, and you're left with just 2 to the negative 1 power, which becomes 1/2. That leaves us with just a 2 in the denominator here. The other way to think about it is really to use one of your properties of exponents backwards, kind of. So 2 to the n over 2 to the n plus 1, the denominator here, 2 to the n plus 1, we could actually use a property of exponents backwards and say that 2 to the n plus 1 actually came from multiplying 2 to the n times 2 to the first, because when you multiply common bases, you add the exponents. By writing it this way, you can see pretty easily that the 2 to the n's cancel out and become 1's, and you're left with that 1/2. Both ways are equally useful. Either way, you end up with the same result. And now we're ready to evaluate this. It ends up becoming infinity over 2, which is still approaching infinity. And since infinity is greater than 1, this tells us that this series diverges by the ratio test. Pretty simple result, but a lot of good algebra in there. Number 2, same idea, perfect candidate for the ratio test once again. So what is the limit as n approaches infinity of the absolute value of 2 to the n plus 1 power over n plus 1 factorial divided by a sub n, which same as multiplying by the reciprocal of a sub n. And if you didn't notice, number 2 is just the reciprocal function from number 1. So this time, when we simplify it, we're left with a 2 in the numerator and an n plus 1 in the denominator, so that when we evaluate this, we get 2 over infinity. 2 is a small number in general, but when you divide it by infinity, which just keeps getting bigger and bigger and bigger, the result of this fraction approaches 0. And since 0 is less than 1, that tells us that this converges. By the ratio test. Again, pretty simple result. We get to number 3 here, and I'm going to expand my screen a little bit here. When we are doing number 3, a little bit more complicated. What is the limit as n approaches infinity of the absolute value of n plus 1 squared times 2 raised to the n plus 1 plus 1 divided by 3 raised to the n plus 1 divided by a sub n, which again is just the reciprocal, multiplied by the reciprocal, of a sub n. And this one, boy, there's a lot going on here. So one suggestion I have when you've got a number of common bases is you may want to rewrite this as one big fraction and you can rearrange the numerator and denominator so that the common bases are lined up. So n plus 1 squared, underneath it I'm going to put the n squared that you see right here times 2 raised to the, let's simplify this right away, n plus 1 is now 2 raised to the n plus 2 power, and in the denominator it's just 2 to the n plus 1 power. And then my base of 3 in the numerator is 3 to the n, and when I rewrite the denominator, it's 3 raised to the n plus 1 power. Two parts of this are pretty self-explanatory. 2 to the n plus 2 over 2 to the n plus 1, similar to some of the ones that we just did earlier. The 2 to the n's cancel out, and 2 to the second over 2 to the first just becomes 2 in the numerator. 3 to the n over 3 to the n plus 1, multiple ways to do it, but the 3 to the n's cancel, leaving you with just a 3 to the first in the denominator. I see lots of mistakes made with the n plus 1 squared over n squared, because students forget that n plus 1 squared, you have to multiply n plus 1 times itself and distribute it out so that it actually becomes n squared plus 2n plus 1 all over that n squared. And because n squared plus 2n plus 1 is not the same factor as n squared, you cannot cancel, and this is as simplified as you can get. So we're ready to evaluate this. There is one suggestion I would offer, and that is 2 over 3 is really just coefficient. So we're going to actually put that 2/3 out front. Not sure what happened there. Let's just try this again. We're going to put that 2/3 and pull that right out of our absolute value bars, so that all we have left in the absolute value bars is n squared plus 2n plus 1 over n squared. Now when we evaluate this, we get 2/3 times infinity over infinity, which is infinity over infinity and a perfect candidate for L'Hopital's rule. So to continue the problem, we reevaluate the limit as n approaches infinity of 2/3 times the absolute value of the derivative of the numerator, 2n plus 2, over the derivative of the denominator, 2n. I see another opportunity here before I evaluate this to factor a 2 out of the numerator, so it becomes 2 times n plus 1. And that way I can cancel my 2's out, so that when I reevaluate this, I get 2/3 times, oh, there it is again, infinity over infinity. Which means L'Hopital's rule one more time. So to finish the problem out, the limit as n approaches infinity of 2/3 times the absolute value of 1 over 1 after I take the derivative gives me simply 2/3. There's no n's left, so I don't have to do any substitution, and since 2/3 is less than 1, that tells us that this series converges by the ratio test. We will use the ratio test quite a bit in the coming days here as we decide whether power series converge at a point, converge absolutely, or converge over an